So I'm going to talk about our little project, which is called Flare, and it's an accelerator for Apache Spark. And in particular, what we're doing is we're compiling entire query plans of Spark to native code, and as I will show you, we're getting some pretty nice speedups by doing so. Just a little bit about myself. So I'm an assistant professor at Purdue University, right? So that's the campus. That's about 2 hours south of Chicago in what one could call flyover country, but it's actually quite pretty, and we normally have much better weather than Chicago. Anyways, before I went there, I was actually a member of Martin's Scala team at EPFL for, I think in total 6 years. And I did a bunch of things around Scala, working on the compiler and libraries and doing a bunch of research. And so this talk really is about a recent project that we did, and we started looking at Apache Spark a while ago. So I guess all of you are familiar with Spark, right? So Spark is this very popular big data framework. And actually, the first time I heard about Spark was at Scala Days in 2011, where a guy named Matej, who was then a PhD student at Berkeley, presented this new library for distributed computations that looked very much like a Scala collections API. And he showed huge speedups over Hadoop, which was then the state of the art in cluster computation, right? And the way they got these speedups was that instead of just having single map reduce phases, where in between those phases you would have to write data to disk and load it back again, Spark would actually allow you to keep data in memory, right? So remove the I/O bottleneck, and you could get speedups of 10x, 20x, 40x, right? Crazy numbers. And since then, Spark has become really, really popular, and in particular, there has been a lot of work in increasing the performance, right? And as I mentioned, Spark started out as basically just being a library, right? But these days, it actually has multiple intermediate layers. There's a query optimizer, right? Much like what you would find in a relational database system. And there's even multiple front ends, so you can have SQL statements as front ends and use it from Python and Java and other languages as well, right? So with all this work that has been done here in terms of performance improvements, the question one could ask is, well, how good is it really, right? How fast is Spark in practice? And I want to do some small experiments here, which are based on a data set from the Google Books website, right? So if you go to Google Books, then you can download a data set that tells you what is the relative occurrence of certain words over the whole Google Books corpus, right? And you can download bits and pieces of this data set. For example, we can take one file which has all the words starting with A and just run some analysis with Spark on this file, right? So this is about 2 gigabytes in size, right? So not something that you would call like super big data, but it's still kind of sizable to do this on a small laptop here. It's going to increase the font size a little bit. And the way we can do this is, well, we have to basically define a schema for this file. So it's a regular CSV file. And we have to tell Spark, well, what are the columns here? And then we can, once we have defined the schema, we can say load this file and also register this as a temporary view so that we can refer to it from SQL queries and data frame operations. So now let's actually run some queries here. So I'm going to load this file, load demo.scala. There's a couple things going on here. And now I can do something like gbooks.filter and let's say phrase equals some word. So I really like John Pretty's April Fool's joke, so I'll pick something in German here. Right. And when I do this, so this didn't, sorry, need to put in the quotes. There we go, right? And when I enter this, then no computation actually happens. So this is just a deferred API, so it will create a data frame or data set, right? And when I actually want to run this, I have to say something like q.show. And let's actually do some timing. Let's figure out how long that will take, right? And just kick this off. So now it will go ahead and start processing, right? And you can see that, oh, that was very fast, right? But actually, this was only fast because it's just showing the top 20 rows, and the string I've been looking for actually occurs at the top of the file, right? So let's do something more interesting. Let's say get us not only 20 lines, but get us a maximum of 1,000 lines, okay? So let's do this, and you can see it already takes a little longer, right? And okay, so starting a couple of processing stages. Looks like it's making some progress, right? But well, we can wait a bit. We can wait a bit more. And actually, this will take about a minute, right? So just reading this 1 2 gigabyte data file. So while we're waiting for the result, let's actually think about what's going on here, right? So maybe for this little query, which doesn't do much, Spark is actually overkill, right? So we don't have to run a cluster computing framework to just go through a file and look for some keywords. So let's actually look at some alternative, right? So here's the same query written as plain Scala code, right? And we've done a little bit of performance optimization here, so we're not using any of the Scala collections, but we're really just creating a scanner, and then there's a while loop which iterates over the scanner and traverses the data, right? So this is something we can do as an alternative. So the Spark query is still running, right? And if we want to go even further and say, well, maybe the Scala code is not quite the fastest we could get, then we might even go as far as writing the same thing in C code, right? And in C code, we can play some more dirty tricks here that are not so easy on the JVM. So one thing we can do is we can use memory mapped I/O and eliminate a whole range of data copies, which we would still have to do on the Scala program. Okay. So in the meantime, the Spark query has actually returned a result, right? And you can see that, well, this was 110 seconds, right? So almost 2 minutes. Right? So now let's actually run this piece of handwritten Scala code just for comparison. So I've prepared a little script here. And let's see how long that will take. Okay, so that produces results faster, but as I mentioned, the rows that we're looking for, they are at the top of the file, so we would expect to get the answer early, but it's still running and looking at all the rest of the file here, right? But it takes only 18 seconds, right? So down from order of minutes to just 20 seconds, right? So that's already a nice improvement. But I also showed you the C code, right? So let's try and run the C code for comparison. So the file is called hand2.c. And so what would you guess? How fast is the C code? Right? What's the delta between running C code and running Scala code for this kind of workload? Say again? 5 to 10% difference? Okay. Any other? 5 seconds? So from 20 seconds down to 5 seconds, do you think there will be a difference that large? Okay, so we got some ideas here. So let's run this, right? And see, well, there we go. And this was, yes, 6 seconds, right? And actually, I think if we run it again, because we're using this memory mapped I/O, the operating system will actually cache the file. So if we run it again, then we're under 3 seconds. Right? So here you get an idea of the magnitude, right? So Spark takes 2 minutes, right? And I think if you run it again, then you will get to 1 minute perhaps. But this little piece of C code takes under 3 seconds, right? So that's kind of the amount of overhead that is inherent in Spark at various levels of the architecture, right? There's this RDD layer for fault tolerance. There's sort of this distributed by default assumption. right? And there's just, even for simple things, when you're running on a small laptop or on a single server, then you have to pay for all this overhead, right? So what I'm going to show you now is that actually we can get the same performance as the handwritten C code using Flare, which is our accelerator for Spark, right? And the only thing we have to do is, so remember we have this query queue defined as some Spark data frame. And what we do now is we just call Flare of queue, okay? And what we get back is a value of type FlareDF. So that's a Flare data frame, right? And this tells the system, okay, when you're running this query, then please use Flare to compile it to native code and run the native code instead of what Spark would do normally, okay? So let's look at this. Let's do Flare of queue.show, and the API is pretty much the same. So now there's a compiling phase, so it takes about 200 milliseconds to compile this code, and you can see you get the result back in 4 seconds, right? And if we run it again, then I think we'll get the result in under 3 seconds as well. Well, maybe not this time, but you get the idea, right? So it's still 4 seconds. Ah, there we go, right? And yeah, so we can use essentially the full Spark data frame API, right? So there's not many restrictions. We just take the whole front end. So for example, I could rewrite this query as a literal SQL statement, right? I can do spark.sql select star from gbooks where phrase is, and then our keyword. Right, so that should, missing a quote, that should do exactly the same thing, right? And we can actually get the query plan printed out, right? So here are all the operators that Spark will execute when you run this query, right? And again, sort of no matter whether we're using the data frame API directly or whether we're using a SQL statement, if we run this using Flare, then the performance is exactly the same, right? Something like 3 seconds or a little bit more, okay? And of course, I mean, we can do more interesting queries as well. So I have one query from the TPCH benchmark, right? So this is a common analytical benchmark, 22 queries, and it's all based on a decision support workload, right? So you have tables for line items and orders and customers and so on. And query 1 is also relatively simple. It just traverses the line item table and has a group by operation, right? So this already means we need to construct a hash table for accumulating the aggregates. And there's also an order by clause, right? So there's some sorting going on in the end. Right, and let's just again run this using Spark and then using Flare. So what we do is val q equals spark.sql tpch q1, right? And then we do time q.show, right? So again, this is running on Spark, plain Spark, and yeah, we can wait again, right? So I think this is going to be a little faster because the data set is slightly smaller. So I think this should be, well, maybe 30 or 40 seconds or something on that order. And once we have the result, we can run it using Flare again, and you will see that the performance will be much better again. Yes? So this is version 2.0, I think. Yeah. Oh yeah, it's absolutely, yes, it's absolutely doing that. Yeah. Yeah, so this is actually one thing that's interesting, right? So Spark actually internally does code generation as well, right? So they generate Java code, and what they have is, as you mentioned, they call it whole stage code generation, right? So if you're thinking in terms of MapReduce stages, then they will generate a Java class for a given stage in a complicated query, right? And so what we're doing goes beyond that. So we're not just looking at individual stages of a query, right? So you can see there are a couple of stages being executed here. But we're taking the whole query and generating essentially one C file for the whole thing, right? So actually this was more than 1 minute, so 85 seconds, right? So let's just, for the sake of completeness, let's do Flare, sort of just to demonstrate that, well, we can do more than just like parsing a CSV file, right? And you can see, okay, here's already the compilation takes a little bit longer, right? But we get the result in under 10 seconds again, right? So again, you can see, well, there's an order of magnitude difference in the achievable runtime. Okay, any questions at this point? Yes, please. So here we're comparing single-threaded performance. So I'm running Spark single-threaded and I'm running Flare single-threaded, but I will show you numbers for parallel performance in a bit.
Do we have any restrictions on the data frame, on the Flare data frame that comes back? I mean, it's a different data frame now. I mean, I guess I have to handle differently. It's different methods probably.
So the methods are largely the same. So right now they're a subset of what Spark provides, right? So we have, I think, a set of the most important methods and internal operators that we support, but there are some corner cases that we don't yet support, right? Yes, please. Yeah. Yeah. Well, it's very hard to point to one specific thing they do wrong, right? There's just sort of in this whole architecture and stack of Spark, right? So there's just many inefficiencies in a variety of places, really, right? So there's obviously at the bottom there's this RDD layer, right? Which means that essentially for every operation that you're doing, you have to sort of carry around the lineage of things, right? And then there's the code generation, which, as I mentioned, they do for sort of stages of a given query, but not for whole queries. So whenever stages have to communicate, then there's some overhead in this communication, right? And there's also, of course, some performance benefits just running native C code versus running on the JVM. Oh, yeah. It goes through Tungsten. It will generate Java code. It will do all the things, yes. Yeah. Good. So that's what I wanted to show you in terms of demo. So now some more background and architecture, right? So essentially what we're doing is if you look at the Spark architecture, then we have various ways of interfacing with that, right? So, yes?
Sorry, just before we wrap up.
Sure.
So Flare only works if it's local, right?
Sorry, say again?
Flare is only when it's local. I mean, if you have a cluster. So you would use Flare whenever like you're testing Spark and you're just testing local.
I'll come to that, right? So we're mostly focusing on single node execution, but it doesn't mean that you can't also run distributed, right? So it's just the way we started this was actually to say, well, what are the inherent overheads, right? And what is the performance we can get on a single box, right? Because if you don't actually use your individual machine efficiently, right, then scaling will only get you so far, right? Sort of in some cases, I mean, if you get 100x speed up on a single box, then that tells you would have to use 100 machines and get perfect scaling to match that performance, right? Which in general is rather unrealistic. Yeah. Okay, so here's what we're doing, right? So we essentially have 3 possible levels of interaction with Spark, and all are based on taking the query plans that come out of the Catalyst optimizer and then doing something more efficient with these query plans, right? So what we call Flare level 1 is still quite tightly integrated with Spark. So essentially where Tungsten would generate Java code, we're generating C code and then linking the C code via JNI into the running JVM, right? But that kind of has the same limitations as what Spark is normally doing, right? So we don't see the whole query and we don't have a global view of things, and we're kind of limited in the optimizations you can do here, right? So So what I showed you in the demo, this is actually Flare level 2. And here we're taking the query plans and replacing the whole backend of Spark, right? So no RDDs involved, no executors, and so on, right? So we're taking full query, generating code, and then running that code either in the same JVM, but sort of very loosely integrated, or even as a separate process when you only want to print out the result. Right? And then the third level of integration is that we take the query plans and then translate them to a more complete compiler framework that we have, right? So this is a joint project with Stanford that has been going on for a number of years. And the system is called Delight, and it's a compiler framework for domain-specific languages. Right? So there's a couple of domain-specific languages that are all embedded in Scala. Those are called OptiML, OptiGraph, OptiQL, and so on, right? And essentially, we're taking the Spark Catalyst query plans as another DSL, right? And then we can translate all of these DSLs to a common intermediate language. And from this common intermediate language, we can generate, well, CPU code again, but also GPU code, and we can also run stuff on clusters using a sort of internal cluster runtime here that's also, in many cases, more efficient than what Spark provides, right? So these are the three levels of integration that we can have. Any questions about this? Yes, please.
I guess this might be a naive question, but say I'm using data sets and
Mm-hmm.
like through Scala constructs like lambdas and
Mm-hmm.
classes. A lot of that goes into like serialization and all that other
Mm-hmm.
business. How does that interact with Flare?
Yeah, so of course we're limited in that sense that we can't easily and we don't want to call back into the JVM from C code that we generate, right? Because then you would lose a lot of performance again, right? But we can write user-defined functions sort of in a stylized API, right? And well, I think I could actually show you an example again for this. So let's say. Right, so in Spark you can do something, you can say, well, square is a function from int to int, right? And then you can do Spark UDF register, I think it's just register, yes. Register square. Okay, and then you could do something like, well, maybe remove the where clause and do sum of square of count A as sum of squares from gbog, right? So this would be one way of using a normal Scala function as part of a SQL query on top of Spark, right? So I don't want to run this because it will take another minute, but basically what we can do in Flare is very similar, only that we have to do something extra for this square function, right? So what we need to do is here we need to get a UDF context as the first argument. And then we have to import context dot underscore, and then we have to change the type. So this was an int, and now it becomes a rep of int. So rep of int is a marker that we're actually constructing an expression at runtime, right? So, and then we need to close the brace here. Okay, there's one extra parent that I missed. Okay, and then we do flare dot UDF register like we would do in Spark. And then let's actually try to run this query. So time flare q dot show. Okay, so this is basically what you need to do for UDFs, right? So you need to provide an API that works with these rep types, and then we're able to generate C code from this. And we can actually look at the generated C code. Yeah, so here's the square operation in the generated C code, right? So it's right there. So it will literally generate just a primitive multiplication from this user-defined function. Okay? Good. So as I mentioned, this is the architecture, and I'm going to focus on Flare level 2. And so basically, we need to understand a little bit how these query engines work, right? So if you look at the normal database system, or also the way Spark is designed internally, you have a query language, you generate a logical plan, then you do some optimizations, you get to a physical plan, and most database systems will then have an integrated interpreter that interprets these query plans over the given data. Right? So if you look at this, then this is really, it looks very much like a compiler, right? So there are translations, optimizations, and so on, but the last step is missing, right? So it's not generating machine code. And this is really what we would like to do here. And of course, the question is, what is the right approach for doing this? And sort of you could take a compiler textbook and look at this, and you will learn all about register allocation and data flow analysis and so on. And well, then you can sit down for 5 years and actually implement this for your query compiler, right? But that's kind of inefficient, right? So the approach we've taken is more inspired by partial evaluation, right? So there's this notion of Futamura projections. And that essentially tells you if you have an interpreter which takes a source program and some input for that program and computes a result, then you can go ahead and specialize this interpreter for a given source program, right? And normally this is sort of, you would think about this as having a separate program which is called mix that does this specialization, right? And then what you're getting is essentially a compiled version of the source program, right? So you specialize the interpreter for a source program, and that gives you a compiled version of the source program, right? Which hopefully runs much faster than applying the interpreter. And so the key insight here is that, well, compilers are not actually fundamentally more difficult than interpreters, right? So at least if you have a compiler backend that you can rely on, right? And so this notion of Futamura projections also tells you that you can mechanically derive compilers from interpreters through specialization, right? So this is kind of a very deep connection here. But the question is how to make this practical, because normally these partial evaluators are very brittle and very hard to get right? And so a more practical approach is actually not to rely on an automatic partial evaluator, but to use a technique that we call staging or generative programming, where you have an API that constructs code at runtime. Right? And in Scala, we can dress that up nicely using operator overloading, implicits, and so on. And this essentially allows us to write the staged interpreter directly without using an automatic partial evaluation system. And I just want to show you sort of a little bit how that works. So the key idea is in this framework which is called LMS, right? So we've already seen this type rep of t for writing user-defined functions, and this is exactly how Flare is built internally, right? So whenever we have a normal Scala type int string or t, then that's just a regular expression. It will be executed right away. And if we have an expression of type rep of int, rep of string, rep of t, then that means that we'll be generating code for this, okay? And there's overloading also for if then else using macros and so on. So if we do this, and we start with a normal query interpreter, right? So here's just showing the core of it. So you have a method execop, which takes a query operator and then a callback. And query operators could be something like a scan, which is sort of just iterating over a file, or a filter, or a projection, right? Then basically all you have to do to turn this interpreter into a compiler is change the internal definition of records, right? So data set contains records, and records contain fields and a schema. right? And sort of when we think about what is part of the query and what is part of the data, then we can see that the fields are actually the only thing that are data dependent here, right? So the schema we know statically, the list of operators we know statically. So when we want to specialize this, we have to mark the fields as the values that are dynamic, right, that we're generating code for. And we do this by just inserting this wrap constructor around the base type of the fields, right? So where we had a vector of string, we now have a vector of wrap of string. And everything else can more or less stay the same, right? So internally, we have to adapt the data structures, but the core of the query interpreter can stay the same, right? And this is also why Flare can integrate so tightly with Spark. We don't actually have to change their representation much. Right? So we just have to adapt the signatures, basically. Okay? And then we can do something more complicated, right? So here's the actual code for a hash join, right? So we're creating a hash map buffer, we're iterating over one table, adding all the values into a hash table, and then we're iterating over the hash table. Sorry, we're iterating over the other table and doing the hash lookups for the values, right? And this is the actual code that you can write, and in a single pass, it will generate low-level C code with specialized data structure implementations to actually run the query. Okay? And there's more things we can do, sort of using specialized data structures, using different kinds of callbacks to move code around in the generated C code, and so on. Good. So now let's actually look at some more performance numbers, right? So these are not just single queries and small data, but this is a larger data set. So this is scale factor 10 for TPCH. So that's a 10 gigabyte data set, and we're comparing running times for all the 22 queries for Postgres, Spark, Flare, and Hyper. Hyper is also a state-of-the-art query compilation system. And when you look at the graph, then you can really see that there are two kinds of systems, right? So Postgres and Spark are kind of slow, and Flare and Hyper are 1 or 2 orders of magnitude faster here, right? So these are, this is a log scale graph here, right? And that's running from data that's stored in memory, right? But most of the time, you actually want to load the data from somewhere. And that might either be CSV files or often something that is more efficient, like Apache Parquet, right? So Parquet is a columnar format, and we have both an optimized CSV parser and also an optimized Apache Parquet parser, right? And here we're showing speedups again, and you can see that, well, you get, again, well, most of the time, at least 2 orders of magnitude speedup over plain Spark. These numbers are, again, sequential, but this time they include all the data loading. Now the question, of course, is parallelism, right? So running things on a single core, even if you're much faster, will only get you so far. And of course, we can also parallelize, right? And first of all, what you see is that the speedup graphs, if you're just looking at the parallel speedups, are a little different between Flare and Spark, right? And in particular, for some queries, it looks like that Spark is actually doing much better in terms of parallelism, right? So this one pink line here, Q6, Spark scales to 32 threads, versus Flare only scales to 16, and then it drops again for 32. Right? So this is something that one can see quite often, right? That systems that have a lot of internal overhead actually scale very well, right? Because this overhead is trivially parallelizable. But if you look at the actual running times, then you can see that Flare is much, much faster on all queries. And in many cases, Spark, even though it scales very well, it will just never catch up, right? Because at some point, it will go up slightly again. Right? And this particular case of query 6 is actually very interesting because we are running on a multi-socket machine, which has 18 cores per socket. So 16 threads, that's still running on a single socket. But once we go to 32, we actually have to use 2 CPU sockets, right? And if you know a little bit about architecture, then you know that modern server-class machines with multiple CPU sockets are structured in such a way that they also have local memory attached to each CPU socket. And if you want to access remote memory, you have to go across the bus, and memory access becomes much slower, right? And this is exactly what we can see here, right? And this actually means that we're running sort of at the capabilities of the machine, right? So we are exploiting the CPU as much as we can, and then memory access becomes the bottleneck, right? Versus in Spark, it's still CPU bound, right? So it doesn't even, the memory latency doesn't even show up. Okay? So once we know sort of this architecture, we can actually go ahead and optimize for it, right? So we can represent the data in a columnar way that is partitioned across the CPU nodes, and then we can make sure using thread pinning and other techniques that most memory accesses will actually be to local memory, right, and not go over the bus unless we have to. And once we do that, we actually see very good scaling for higher numbers, of course. So on the right, again, this is query 6. And you can see that for 72 cores, we still get a speed up of, 58, right? So that is pretty good. And what is interesting, actually, if you look at this graph in more detail, is that if you look at these bars here, right? So here we're running with 18 threads. And this bar is 18 threads on a single core, right? And if we use 18 threads on a single CPU socket, right? And if we have 9 threads on each of 2 CPU sockets, then we're actually running faster, right? Because now we have a higher aggregate memory bandwidth that we can use, right? So it's very important to do these architecture-aware optimizations, and depending on your workload, you can get either a large slowdown on these big machines or actually get a large speed up. And since we're generating C code, we have all the options of exploiting these things, right? So we can access any system API and so on, which is much more difficult when you're running on the JVM. So this is Flare level 3. This is integrating some relational processing using data frames with some DSLs for machine learning. So here's some machine learning kernels, logistic regression, and k-means clustering. And, well, don't have to go into details, but you can see, OK, this also scales pretty well on NUMA machines. And we can also scale pretty well on clusters of machines. So this is a 20-node Amazon cluster on the left and center, right? And you can see that, well, you're getting speedups of still like 3 or 4 or something, right? But this is sort of including the machine learning computation, right? And we can also generate GPU code. So this is a smaller cluster of just 4 machines here. But there again, we have speedups of almost an order of magnitude, right? So 7 or 8. Good. So this brings me to the end of the talk. So I think, a key lesson for all this is that, as we already know, right? So any problem in computer science can be solved by another level of indirection. And here the level of indirection is that you're generating code, right? So instead of doing things at runtime and just trying to optimize bits and pieces, just generate code for a full query, and it will run much faster. I should also mention that since we've been looking at Spark, one new thing that we're doing, we just got a project funded by Google, is to also look at TensorFlow, which has a very similar API, but not for relational things, but for linear algebra, right? But it's the same idea. You have a deferred API that constructs a computation graph, and then you can look at this computation graph and actually generate code and hopefully do something more efficient. And one thing that in particular we'll be looking at is the integration of these two systems, right? So we want to have pipelines where you can do some pre-processing of data using Spark and then feed it into a machine learning pipeline that's written in TensorFlow. But this is kind of future work here. In any case, I should mention that most of the actual implementation was done by my students at Purdue. And we have a website, and we also have a private beta program, right? So if you or your company is running Spark and you're thinking, gee, this is taking so much time, we would rather save some of the time, then, well, please come talk to me. And also there's a contact form where you can leave your details if you're interested. Thank you.
targeting generating C rather than targeting LLVM? How is the decision made there?
Oh yeah, that's an excellent question. Yes. So I think one key benefit of actually generating source code is that you can go ahead and read it, right? And that's immensely useful for debugging, right? And even though the code is not, well, it's not super pretty, right? But you can actually, I mean, if you want to understand what's going on, right, then you're able to, right? And I'd much rather look at C code than at a dump of LLVM assembly. Right? And we can also, since we're generating code explicitly, we can generate all kinds of debug information in the source code, right? So we can say, well, this line comes from this operator, which is the join between these two data frames, and so on, right? So that is very helpful. And of course, obviously, LLVM would get us slightly better compile times, but I don't think that it's actually a very big difference, right? Because most of the time the C compiler spends is doing in backend optimizations, right? And that's something that LLVM would also have to do, right? So maybe you would get, I don't know, 200 milliseconds per query, right? But that sort of seems like a trade-off worth making. Yes, please.
How specific is this to Spark? Could I rip out some of these libraries and apply them equally to Scala code that I was compiling on my own box for whatever purpose?
So it's not very specific to Spark, right? But it's, so what I showed you is kind of specific to a relational query plan, right? So if you're taking, let's say, Scala collections as input and you're able to generate the equivalent of a logical query plan from that, then yes, we can just take that as input.
The follow-up to this, did you guys look at using it for Hive? Because there is still, the majority of people are using Hive, not Spark SQL.
So I think much of this would also apply to Hive. We've looked at Spark because that's what we cared about, but I think it should pretty much be doable to do the same thing for Hive. Yeah.
And the other question, TensorFlare, where can I look up what you guys are planning to do on this?
Yes, I think it's a bit too early to talk about TensorFlare, but I think yeah, that's something that we'll be looking at.
Because Google is doing C++ generation anyways.
Yeah, so they have this XLA thing, which is the just-in-time compiler for TensorFlow, yeah. And I don't think I think they're only generating C++ wrappers, but they're actually generating LLVM as far as I'm aware, and CUDA code for GPUs, yes. Any more questions? Yes.
So are there any trade-offs? Like when would someone choose to use vanilla Spark and choose to use Flat?
So I think if you most of your workload is actually calling back to existing Scala libraries, right? Then there's not much we can do, right? So in that case, if that is really what you're doing, then yeah, then you probably just want to use normal Spark, right? Because sort of what we're doing is not going to be able to accelerate the code.
Have you guys discussed, or have you been in contact with the folks who are working on Scala native, and whether or not this would be able to potentially have some interop there? The idea being that you might be able to compile Scala native and this together and then eliminate some of the problems with interop.
Yeah, so that's a very good question. Certainly something that could be explored. I think much of the benefit we're getting is from the fact that we're not compiling a full language like Scala, right? We're compiling relational query operators, right? If you work to compile all of Scala, then you would have to reason about functions, about classes, and so on, right? So all the kind of modularity abstractions that you have in a full language, right? So
right. Well, I read my group uses Spark SQL heavily, but we have a strong reliance on UDF functions. Mm-hmm. So making a jump like this would require us to throw away a huge amount of existing work. No? Well,
no, but he was showing how to convert.
Oh, but, well, also, then correct me if I'm wrong, my impression was that the rep boxing only works for simple types that are representable in C.
So you can, so by default, I mean, it works for simple types, right? But you can build elaborate APIs using these rep types, right? So the kind of stuff I showed you with machine learning, right? So we have libraries for vectors and matrices and training sets and so on, right? So which basically look like NumPy or MATLAB or something like this, right? So you can construct pretty elaborate things using these staged APIs.
Okay. Another question, when you were running this on Amazon, how much libraries did you have to push on every node? So how heavy is dependency if I want to run this on my machine?
How heavy is the dependency? Well, you need a couple of jar files, right? And
well, I'm sure you're using some C libraries under the covers.
So we don't use a lot of C libraries. So we just basically use the standard library, and most of the data structures are custom generated, right? So we specialize data structures with respect to the schema and so on, right? So we don't use STL or Boost or anything like that.
Right, that is the main question. Depending on the operating system and everything else, how much do I have to tweak it?
Yeah, no, on the C level, not much. So I mean, you could, right? So that's another potential answer to the UDF question, right? So if you have libraries in C or C++ that do the same job as some of the code you would be writing in Scala, then it's very easy to call those from generated C code, of course.
This line here seems a little bit magic, but how did that Scala square function get translated?
Oh yeah, so that's well, basically we can look at this again, right? So this was the definition of the square function, right? And so x has type rep of int, right? And there's an implicit which provides a times method and other arithmetic methods, right? So that the result of adding or multiplying rep of int values is a rep of int again, right? And internally, rep of int is a term representation that says, okay, this is an integer plus.
So some of the magic is tied into the rep.
Yeah, yeah. So this is part of the
How
core.
complex a function can you translate?
You just have to define you have to define the language that's available, right? And then you can write any program using this function, right? So we have stuff, I mean, so I'm not sure if I have the k-means code here, but we can write like machine learning kernels like k-means or anything, and that's like 50 lines, right? And we can use abstractions for vectors and matrices and all these kind of things, right? So as I mentioned, so you can build very elaborate things using these kind of APIs.
I was looking at that page. There's some magic.
Yeah, well, it's all implicit, right? So good, I think we should wrap up. If there are more questions, then please come talk to me during the break. Thanks again.